Hi everyone, this is the first in a long series of videos that I hope to record for the full course of Stats 200 at the University of Maryland Global Campus. I'm currently teaching the class. I just started teaching it, and it's a very, very big and demanding class, and I wanted to help my students by recording little video snippets of each section to kind of make the material a little easier to digest and to point out the important stuff that will be tested. Now, it's going to take me probably at least a year to really finish going through the course in video format. But I'll go ahead and post it online while it's in progress, and it'll be accessible to everybody whether you're in my class or not. So these videos will probably be useful for many different stats courses, but keep in mind that they are going to be specifically keyed to UMGC Stats 200. I have chosen not to display the textbook on the screen, although that would be really helpful because of copyright issues. I don't have copyrights to the book, and I have to admit I've gotten into copyright trouble before on YouTube. I had an entire channel taken down by a test prep company one time. So I know that that's a real hazard, and I'm not going to risk that again. So you can certainly feel welcome to follow along with the book on your screen. This video will be for section 1.1, which is roughly pages 2 through 9, 1 through 9. Okay, so this is basically the lecture outline that I'll be following, and I'll be demonstrating some of this on the whiteboard, as you can see. So in this section, the main themes that I want to address are gathering data, representing and analyzing data, and percents. So let's start from the top and talk about what data is and the issue of gathering data. So let me go ahead and blow up my my whiteboard webcam here. So the way I've defined data is observations from a sample about a population. So what do samples and populations mean? A population is a very large body of people or things that we're interested in learning about. A population is usually too large to observe directly. It might, for example, be all American women, or it might be all children under the age of 10. Or it might even be something like all bacteria that have ever lived. So it could be immense. How do we learn about a population? That's a really interesting question, because populations are usually too large for any person or group of people to observe directly. So we have to do with the next best thing, and that is we have to be able to work with what we can reasonably observe. So what we generally do, what statisticians do, is they will cut out a small, relatively large but manageable part of that population, which they call the sample. You can almost imagine this like a little biopsy. Like if you kind of think about your population as being an organism and you want to learn how it's doing, you can take a little scalpel and cut out a little sample, and if you study that sample, it should be telling you something about the population. So essentially, when we observe, we are directly observing really only the sample. And the observations of that sample are what we call our data. Data is very often numbers. It doesn't have to be, though. It could be different things like categories. And in future sections, we'll break that down further. There are many different ways to categorize data. For this section, for some reason, the only category that they brought up was the issue of matched data. So let me address that a little bit right now. Matched data means that when you go into the sample and you observe something, you actually observe two or more things about it at the same time. A typical example would be that maybe your population is married couples, and you want to learn something about the duration or the health of their marriage or their income or something. So every time you sample a couple, you might observe something about the husband and then also something about that wife. And you would keep those data points side by side. So you might have something like couple number 1. The husband's income is $85,000 and the wife's income is $102,000. Couple number 2, 60, 48. Okay? So basically every pair of observations here is matched. The husband is matched to the wife. When we observe a sample, are we really learning about the population? We want to make sure that we're not just learning about this little sample, because that wouldn't be very interesting. We don't want to just learn about 600 couples. We want to learn about all of them in the whole world, even though we can only observe 600 of them. That kind of seems like magic, doesn't it? How could you just observe 600 couples and then make a conclusion about all the couples in the whole wide world? Well, that question comes down to whether the sample is properly representative of the population. What does that mean? Well, in a nutshell, it basically means that the sample that you took is large enough and random enough, randomly selected, so that it is a microcosm of the whole population. The question of whether a sample is large enough or how large the sample should be or what the limitations are if the sample is of a certain size is a thread that's going to run through this whole course. We're going to spend a lot of time talking about issues of uncertainty that surround samples, because there's always some. A sample is never a perfect picture of the whole population. So then the important question becomes, how close is it and how sure can we be? So we're basically going to spend the rest of this whole course talking about those issues. A secondary issue that really is only addressed in the early parts of this course is how random the sample was selected. Now, in this course, in this section, I should say, all we really need to remember about randomness is that we should avoid what's called voluntary response samples. A voluntary response sample is where you basically put out an announcement. The statisticians would put out an announcement, say, hey, anybody who wants to answer our survey, please go to this website and fill in the questionnaire. And maybe like if you fill out our survey, we'll give you a free subscription to Stats magazine for a year. So rather than going out into the field and knocking on doors or calling phone numbers at random, they're just putting a call out there and saying, we will accept responses from anybody who wants to. And when we do that, it raises issues that the people who respond to the survey are really not very representative of the population. They're only the ones who are excited to answer the questions. So that would be an example of poor sampling. I think the book calls it a misuse of statistics. Okay, let's go on to the next issue of representing and analyzing data. Okay, so when we collect data, what we usually end up with on the page is long lists of numbers, and they're really boring and very difficult to read or make sense of. So they must be summarized somehow. One of the most common ways to do that is by making graphs or visuals. As this section of the book points out, we must make sure that graphs are not misleading. What might that look like? They give an example on page 2 of your textbook, by the way. But here's another picture. Let's suppose that we are asking people whether they prefer brand A or brand B. And we present this graph. If you look at that graph, it looks like, wow, brand B is way more popular than brand A. Just look at how that bar towers over the other one. But do you notice anything about how that graph is scaled? It's kind of cut off here, right underneath 49%. 49, 50, 51%. That's not really a fair scale, is it? This would be a more fair representation if we actually make the scale go from 0 to 100%. And when we put those bars side by side, the 49 and the 51 actually look pretty close to each other. I see what you're trying to do there, brand B marketers. So we got to watch out for misleading graphs. It's another misuse of statistics. The next issue involves significance. In other words, that kind of means, all right, we have some data, now what? So what? What does the data mean anything important? Is it significant? Well, that word significance has a slightly different meaning in statistics world than it does in ordinary life. Practical significance is the plain, ordinary, everyday meaning of the word, a result that matters to people. If you're looking at weight loss programs, if one program can offer a weight loss of 20 pounds, wow, that's practically significant. That would really change my lifestyle. Statistical significance means something different. That's really more important to statisticians than to ordinary folk. But statistical significance means that we've proven a result, or we've demonstrated a result that is unlikely to occur by chance. In other words, that means, well, there must be something to it, because we've observed something happen that probably wouldn't happen at random. So we must have demonstrated that there is, in fact, some kind of effect going on. And an example of that might be a diet where it's very clearly demonstrated that people on this diet do, in fact, lose weight, but maybe an average of only a half a pound. So that might be unlikely to occur by chance, because if left to their own, most people will probably gain weight, not lose half a pound. But losing half a pound is not really exciting or monumental to us, so we don't care very much. So there is a difference between those two kinds of significance. When we analyze data, we must watch for data being presented to us from biased parties. Make sure that the information that we're getting about cigarette safety is not coming from cigarette companies. Another issue brought up in this section is that correlation does not prove causation. You've probably heard that phrase before, but you may or may not know what it means. Correlation between two variables means that they kind of go together in a pattern. When one of them goes up, so does the other one. So you might think, for example, that something like a child's age and his height. As a child's age goes up, so does his height. And in that case, that correlation is basically caused by the child aging. As a child ages, he just naturally grows. So that would be an example of causation. But then you might look at another set of data, and you find that, this is interesting. The taller a man is, the larger is his zip code. Well, even if we could demonstrate a correlation between height and zip code, I think we'd have to agree that that doesn't necessarily mean that being taller causes you to live in a different zip code, or vice versa. Sometimes variables are correlated to each other either randomly or maybe because they're both dependent on another factor, like time or poverty. Poverty is a very common lurking factor as well. It doesn't necessarily mean that one variable caused the other. The final issue, and I just have a minute here to wrap this up, is percents. Percents, as you might have expected, are going to be a big part of this course, but we don't have to dive deeply into the kinds of percent change problems that you struggled with on the SAT. We really only have to understand the basic idea of a percent as a proportion. A part over a whole is the percent over 100. And I've prepared a whole separate little video for that theme, so I'm going to go ahead and hand you over to that video at this time. So other than that, that does it for section 1.1. And I'll see you here again for the percents video and then for section 1.2.